So here we go. Okay, so what we have here is we actually break up the equations for you, all right? We actually tell you what each of the individual equations are, and we have y equaling u and a u equaling x equation. So once again, if you were to ask for dy dx in the question, well, we know that that's equal to dy du over du dx because, once again, technically the du's could cancel, and you can see how that equation with fractions there would be correct. And also notice that dy du is the derivative of this. The derivative of the second equation, because it's a u equals x equation, it would be du dx. So let's do this. Okay, let's get the derivative of each part. All right, dy du would just be 6u. Okay, just using power rule. Du dx would be 1, all right, because notice here, okay, u is equal to x plus 2, derivative of that is 1. And we're kind of finished, all right, we found the derivatives. The only issue here is that on the left side, you're given dy dx is what you're asked to find, but on the right side, on the equation, there's no x's. Your denominator letter should be what's on the right side. So what I do is I use this u is equal to x plus 2. I plug that in. So I really have dy dx is equal to 6 outside of x plus 2. And I can put in the times 1, but that's kind of irrelevant. And now we have our answer because our denominator letter, the x, is what's on the right side of this equation. If we look at this example, it's the exact same thing, except with one extra step. We're asked to plug in 1 for z. We do that after. That's like a bonus step in the end. After we get our derivative, then we plug in the number. So notice here, okay, once again, okay, I'm asked for dv dz. So notice that dv dz is what I'm asked for. And I'm given two separate equations. I'm given a v equals x. So that would be dv dx. And then in the second equation, I'm given an x is equal to z, so that would be dx over dz. And just a reminder, you could cancel the dx's, and you could see how this equation is legit. All right, so basically what you want to do is make sure that you have your equations in Leibniz notation set up correctly, and then you're ready to proceed. So now what we can do is we can say, okay, dv dz, let's get dv dx. So let's get the derivative of this equation right here, which is chain rule. Bring the 2 down in front and subtract 1. We can put a 1 there if you want, not necessary. Times the derivative of the inside, which is 3. So that takes care of the dv dx. The next part, the dx dz, is the derivative of this. Derivative of that is just power rule, so that's 3z squared. Technically, I'm finished, but because my denominator letter is a z, I want everything in terms of z's. So I have to go back and I have to replace these x's. Well, there's only one x, so I'm going to replace it with z to the 3 because x is equal to z to the 3. So I should only have z's in here. And then from there, okay, I can simplify this as much as possible. So the most that I can do here, I have 2 times 3 times 3, that is 18. I have z squared outside of 3z cubed plus 1. Or you could distribute through the brackets. You could do that much as well if you choose to. Either way, okay, we would normally be finished, but we have this new thing happening up top where we're asked to plug in 1 for z, and it can be done using the notation on the left where they just tell you what the variable is equal to. Or you could see this notation, which you see on the right, where you see this vertical line and then the z equals 1 below it. It's just another way of saying the same thing. So I need to evaluate, all right? So I need to plug in 1 for z. So I'm just doing my order of operations here. And if I work this out, okay, I end up with 18 times 4, which is equal to 72. So anytime you're given that x or z or whatever is equal to a number, then your answer will be equal to a number as well.